right? So again, we want to get to this point. This is the maximum within block distance. How do we do it? I don't like black boxes. I want to give you some hint of the algorithm, right? So it's going to partition this graph, right? So this graph is like this. It has all these lines everywhere, and I got to partition them. So what it's basically going to say is some of these vertices, some of these data points, going to be separated from some others, which in graph lingo means that some of these edges got to be dropped. These lines got to be dropped. And when a line is not there, it says it's not in the same block, right? So what I'm going to start off is by creating what's called a bottleneck subgraph. What a bottleneck subgraph is, it's a fancy word of saying, all right, for every point here, only draw the lines that are at most, say, what number do I use? 5 points of distant, right? So if the distance between any 2 points is greater than 5, remove it, right? And then the graph looks like that. You lose a lot of the dots, right? And I go, so I want a weight of 3. So if the distance between any of the points is greater than 3, drop them, right? So then I lose some more points, right? And what ends up happening when I have this bottleneck graph is that some points still remain connected with edges. So I dropped all the connections with a weight of greater than 3. A point A and B, which are pretty far from each other, are still connected. They're connected through this path, right? Right, and then we're going to use that in a bit. So what we do is we create a bottleneck subgraph. We pick the maximum weight. How do you pick the maximum weight? Well, you can look at every observation, and if you ask for T star in a block, you could say, all right, what's the maximum distance between every observation and T star minus 1 other observations, right? And I'm going to take that as the maximum. And I'm going to create a bottleneck subgraph based on that maximum, and I'm then guaranteed that everyone is connected to at least T star minus 1 blocks, right? So then, if I do this for this data set, for t equals 2, I end up with this. So now I picked a small enough weight that I got lack of connections, right? There's no path from this to this to this to that. These are now 4 separate blockings, right? But they're not complete, right? So in the sense that this dot's connected to this dot's connected to this dot, but these two are not connected. They're not in the same block yet. This is already a completed block. That's a completed block. This one isn't. These dots are connected to that dot's connected to that, but they're not connected to each other. So the next thing you got to do is you got to pick a center for your blocks, right? And the way you pick your center for your blocks, it doesn't matter a whole lot, but the way we do it is you sort your data, you start from the edge of your space by your measure, and you make the most edge point the center of your block. And then what you do is you say, all right, that's the block center, and then anything that's connected to that with 2 edges, with 1 edge, so it's going to be in these cases 2, can't be a block center, and keep moving in until you have block centers, right? And that's going to induce 1, 2, 3, 4 block centers. 1 there, 1 there, 1 there, 1 there, right? And by the algorithm I just described, the block centers will not be overlapping, right? So you'll get disjoint block centers, right? And then once you have disjoint block centers, right, you say, okay, everything that's connected by a single edge, I'm going to block it together. So this is connected by a single edge, that's connected by a single edge, that's what's connected by a single edge, so those are now together, this is together, those are now together, the block center there, 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 right? So that point is still free out there in space, and it's still have an ambiguity on this one, right? So at this point, once I do this, all the blocks will have at least T star units. But I'm going to have things that are like left hanging out. So I asked for a blocking of at least 2, but this third one's still hanging out there, right? So then you say, all right, for any unassigned vertice, which was this one, assign it to its closest block center. So that one then gets connected to this one, because that one's the closest block center, right? And that's the algorithm. The key thing that makes it go fast is that creating these bottleneck subgraphs, you can do that in polynomial time. I can do that quickly, right? And once I've done that, the rest of it works pretty quick. And that's how I get to this. And as I said, the worst the algorithm can do, even though it's very quick, there's nothing random about it, is so I can replicate this. You give me your data, I can get the same blocking as with my, on your computer, et cetera, and it's going to be very quick. It's often, I'm not guaranteed the exact optimum. I'm guaranteed that I'm going to get this at least 4 times the maximum. And I'm not going to go through the sketch of the proof unless someone asks me the Q&A, so I'm going to leave it open for Q&A. The intuition with the proof is that I started creating these by going out like one edge here, one edge here. And so in the worst case scenario, right, the way to go from any unentangled, unassigned vertice to the block center is going to be another 2 edges. So you get a maximum of four steps. And every step must be at least lambda, which we can show, which is the optimum. And then at worst, you're going to have to take 4 steps from any 2 points, and that's going to give you the 4 times.